Artificial neural networks are machine learning techniques inspired by the learning mechanisms of biological systems such as the human nervous system. They are composed of interconnected neurons that use weighted connections to process information. Each neuron evaluates a function of its inputs and passes the result forward through the network. Learning occurs by adjusting these weights based on feedback from training data, which consists of input-output pairs representing the function the network aims to learn. For example, image-based datasets may include pixel values as inputs and labeled categories as outputs. By comparing predicted outputs with actual labels, the network measures errors and uses them as feedback to refine its internal parameters. These errors play a role similar to negative feedback in biological organisms, where synaptic strengths are modified to improve future responses. In neural networks, weight adjustments are made iteratively across many training examples to gradually improve prediction accuracy. Through this process, the network learns a function that increasingly aligns with observed data. A critical capability of neural networks is generalization, which refers to their ability to make accurate predictions on previously unseen inputs based on limited training data. This capacity to transfer learned knowledge to new situations underpins the effectiveness of machine learning models. Concepts drawn from neuroscience have significantly influenced the development of neural network architectures, reinforcing their importance in modern artificial intelligence. In practical applications such as image recognition, convolutional neural networks have demonstrated remarkable performance. However, they often require large volumes of labeled data and can lack transparency, making their decision processes difficult to interpret. In contrast, traditional machine learning methods may still be preferable in scenarios where interpretability is essential or data is limited. This suggests that combining deep learning approaches with classical techniques can sometimes yield more effective and reliable solutions. Neural networks function as computational systems that map inputs to outputs using structured graphs. These graphs are typically directed and acyclic, with computations at each node determined by incoming values and associated weights. A network's overall behavior emerges from a sequence of function evaluations across its nodes. Simple networks connect inputs directly to outputs, while more complex multilayer networks include hidden layers that enable the modeling of intricate relationships. The primary objective is to learn appropriate weight values so that the network's output matches observed training examples. Activation functions play a central role in neural networks by introducing nonlinearity, which allows the model to capture complex patterns in data. Common activation functions include sigmoid, hyperbolic tangent, and rectified linear units. Loss functions quantify the difference between predicted and actual outputs, and optimization techniques such as backpropagation adjust weights and biases to minimize this loss over time. Nonlinearity is essential because it enables neural networks to combine simple functions into more powerful representations, which is particularly important in tasks like image and speech recognition. Multilayer neural networks, including perceptron-based models, consist of input, hidden, and output layers. These architectures are often trained on large benchmark datasets, such as ImageNet, which has driven major advances in computer vision. The internal representations learned by hidden layers, especially those near the output, serve as powerful features that help the network distinguish complex patterns. By analyzing these features, neural networks can achieve high accuracy across a wide range of applications. Ultimately, neural networks are best understood not merely as biological analogies, but as parameterized computational graphs that perform recursive compositions of simple functions. The central challenge in training these models lies in optimizing their parameters to minimize a loss function. While basic neural networks resemble traditional models such as linear regression, their true strength emerges from deeper and more sophisticated architectures. The use of backpropagation for efficient gradient computation is a defining advantage of the neural network paradigm. Continued progress in fields like natural language processing and image recognition depends on carefully designed architectures, including recurrent and convolutional neural networks that fully exploit the expressive power of deep learning. The backpropagation method is a fundamental learning technique for multilayer neural networks and was widely popularized by Rummel Hart and colleagues in the 1980s. Before its adoption, neural networks were constrained by limited theoretical understanding and insufficient tools from control theory, which hindered their practical development. The introduction of backpropagation renewed interest in neural networks by providing a systematic way to compute gradients and update parameters. Despite its success, early implementations faced challenges related to high computational cost, numerical instability, and overfitting. Over time, improvements in data availability, increased computational power, and refinements to the original backpropagation algorithm have significantly enhanced its effectiveness and practicality. This chapter explores the abstraction of computational graphs, emphasizing a vector-centric view of learning, along with feature preprocessing, weight initialization, and the interpretability of backpropagation. Computational graphs provide a structured way to represent complex functions, enabling efficient calculation of derivatives required for optimization. The chain rule plays a central role in this process, allowing derivatives to be computed between connected nodes and propagated backward through the network. This mechanism makes it possible to efficiently update model parameters, improve prediction accuracy, and learn complex patterns from data. Backpropagation relies on dynamic programming principles to transform intermediate derivatives into loss-to-weight derivatives, which guide parameter updates. The discussion includes important derivatives of common activation functions and how updates differ across activation choices. A vector-based formulation of backpropagation simplifies calculations and improves computational efficiency, especially for large-scale models. Calibration methods and pre-processing techniques are also examined, as they contribute to faster convergence and more stable training. In practice, several additional considerations influence the success of backpropagation. These include mini-batch stochastic gradient descent, learning rate schedules, verification of gradient correctness, regularization strategies, appropriate loss functions for hidden layers, and effective parameter update rules. Feature pre-processing and proper initialization further enhance learning stability. While computational graphs and backpropagation are powerful tools, improper use can lead to overfitting or unnecessary complexity. Relying exclusively on advanced optimization methods may sometimes overlook simpler techniques that can achieve comparable performance with reduced computational burden. Careful balance and informed design choices are therefore essential for building robust and efficient neural network models.